Today we're going to look at exponential functions, specifically how to graph them. So we will see our first example is we want to graph 3 to the x power. 3 is our base, and all exponential functions come in the form of a times b to the x, if you will, and we'll add a little to that in a moment, where b is that base. If the absolute value of this base is greater than 1, we say this is an exponential growth type problem, and if the absolute value of this b is less than 1, in other words, some fraction between 0 and 1 in absolute value, we say that's a decay. So we're going to be asked to graph this, find its domain, range, and state its horizontal asymptote. Only way to do this, if we haven't ever done it before, is to take and make a chart. Let's pick some numbers here. I can put a 0 in. Anything to the 0 power is 1. 3 to the first power is 3. 3 to the second power is 9. What about negatives? 3 to the negative 1 power is 1/3, and 3 to the negative 2 power is 1/9. So I can graph all those points. Here's 0, 1, 1, 3, 2, 9 puts me around here. Negative 1 and 1/3 is about here, and negative 2 and 1/9 is a little lower than that. So you'll see that since that base number was a positive number, we call this a growth, and you'll see that it rises very rapidly. That's the characteristic of all exponential functions, and it appears, and actually is, that we have a horizontal asymptote here, and that horizontal asymptote is going to be along this line here, which is the line of y equals 0. My domain talks about what are my possible x values. Well, you see that this arrow goes to the right forever and to the left forever. So in this case, we have all reals. My range talks about my y's. I go up forever, but you notice here that I don't go down forever. In fact, I have an asymptote, or a borderline, if you will, at y equals 0. So I know in this case y is greater than So for my range, we'll look at the function and say, hey, my y goes up forever, but it doesn't go down forever because of this asymptote or borderline. In fact, it will never. What power can I raise 3 to? What power can I raise a positive number to get 0? That never happens. So y has to be greater than 0 for my range. The horizontal asymptote, as we already stated, is this horizontal line of y equals 0. So now we're going to do some things to these exponentials, and we're looking at HK form once again. So we'll notice that h in this case equals -5, and k in this case is equal to -2. So what that does is it takes and moves my origin over 5 and down 2. So I'll do a little crosshairs there. I'll make up a new parent function of 2 to the x, plug in some values. I'll go -2, -1, 0, 1, 2. 2 squared is going to be 4, 2 to the first is 2, 2 to the 0 is 1, 2 to the negative 1 is 1/2, 2 to the negative 2 is 1/4. And I'll graph that all from this point here. So here's 0, 1. Here's 1, 2, 2, 4, negative 1, 1/2, negative 2, 1/4, like so. You notice this base number is not quite as big, so this graph is not rising as quickly, but it's still rising. So it's a growth problem. It appears that my horizontal asymptote is right along this horizontal here. So that has an equation of y equaling negative 2. Domain, it appears I'm going to the right forever and to the left forever. So again, this is all reals. But my range goes up forever but not down forever. It stops right at this asymptote line. So it appears that y is greater than negative 2. So in this example, you'll notice we have this a term right out in front here. This will be our y multiplier. So if we make a table for this, we'll have a parent function of 3 to the x. And start plugging in negative 2, negative 1, 0, 1, and 2. Plug in negative 2, we get 1/9. Negative 1 gives us 1/3. 0 gives us 1. 1 is 3. And 2 is 9. And that's for our x's and y's. Then we multiply by that y multiplier of 2, giving us 2/9, 2/3, 2, 6, and a big guy of 18. And we're going to look at our a, which we said was 2, our h, which in this case is this negative 1, and our k, which is negative 9. So going over 1 and down 1, 2, 3, 4, 5, 6, 7, 8, 9. We have this new origin, and from that origin we will graph our x's versus our new y's. Alright, so I'll go over 0 of 1. Actually up 2, sorry about that. Over 1 and up 6. And then over 2 and up 18. So if I go up, that was 9 down, another 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's my 18. Go back 1, up 2/3, and back 2, up 2/9, which is really close to that line. Graphing that, something similar to, whoops, this got a lot of lines there. You get the idea though. Now notice once again, we will never go through that horizontal line right here. The domain, you'll notice this goes to the right forever, to the left forever, so this is all real numbers. The range goes as low as the k value, but never touches it, so y has to be greater than negative 9. The horizontal asymptote is that k value, and it's a horizontal line, so y equals negative 9. So in this case, we've got a decay problem because his base is a number whose absolute value is less than 1. It appears that this is a b value, and then we have our h and k, so h equals -5, k is equal to 8, b is equal to 3, and a is actually equal to -1 because I have this negative out here. My exponential is 1/2 to the x power. Don't be afraid of the fraction. Plug some numbers in, -2, -1, 0, 1, and 2 again. 1/2 squared is 1/4. 1/2 to the first is 1/2. Anything to the 0 power is 1. 1/2 to the -1, take the reciprocal, so that's 2. And 1/2 to the -2, take the reciprocal and square, so that's 2 squared or 4. So now I'm going to move back 5, 1, 2, 3, 4, 5, and then up 1, 2, 3, 4, 5, 6, 7, 8. Start from the crosshaired here, but now I have an x multiplier and a y multiplier. So I'm going to do that in each of these cases. My x multiplier is 3, so I have -6, -3, 0, 3, 6, and a y multiplier of -1. So I have -4, -2, -1, -1/2, -1/4. I'll do all that from this point right here. So I go back 6, down 4, 2, 3, 4, 5, 6, down 1, 2, 3, 4. I'll go back 3, down 2, 1, 2, 3, 1, 2, 0, -1, over 3, down 1/2, and over 6, down 1/4. So in this case, the domain, it appears to be going both ways once again, so this is all reals. The range, however, in this case appears to go down forever and only goes up as high as this value here, which is 8. So horizontal asymptote is y equals 8, and y is less than 8. Now, within these exponential growth and decays, we have a general equation as well that can be written as c times 1 plus r to the t power, where y is our final amount, c is our initial amount, and we call r our growth and decay rate, and t is time. So we're going to do some application problems involving this. We see the pressure of the atmosphere is at 14.7 pounds per cubic inch at the Earth's surface. We decrease that by 20% for each mile of altitude up to 50 miles, and they want us to write an exponential model for the situation and estimate the atmospheric pressure at an altitude of 10 miles. Right? So once again, we have the following equation of y equals c times 1 plus or minus r to the t power. And our initial amount is going to be at 10 miles. This 50 is just here to confuse us because this equation only works with this 20% up to 50 miles. Then the equation is going to change a little bit. And So in this example, we know the pressure of the atmosphere is about 14.1 pounds per cubic inch at the Earth's surface. Decreases about 20% for each mile of altitude up to about 50 miles. And we want to write the exponential model for this situation and estimate the atmospheric pressure at an altitude of 10 miles. So in this case, we have an initial atmospheric pressure of 14.13 at the Earth's surface. And that's going to decrease by 20% for each mile above So in this case, pressure of the atmosphere is 14.7 pounds per cubic inch at the Earth's surface. It decreases about 20% for each mile above an altitude up to 50 miles. And we want to write the exponential model for the situation and estimate the atmospheric pressure at an altitude of 10 miles. Well, we have y equals c times 1 plus or minus r to the t power. Now in theory, this talks about time, but we have no time in this problem, so miles is going to act as our time, because for every mile we raise another percentage. So that's going to increase like t would increase, but this is again in miles. So we start off with 14.7 as our initial amount. We're raising 20%, so that's plus 0.2 for every mile we increase. So we'll call that our t, and that gives us our y. This is our model. And then we can solve that model by plugging 10 into the t value. So we have 14.7, 1.2 raised to the 10th. And then we can evaluate that on our calculator. And that gives us about 91.0, let's say 2 if we round to the 100th, pounds per cubic inch. Similar problem, we've got number of wolves in the wild increasing at a rate of 3.5% per year. So now the t is going to reference years. Your environmental studies class has counted 42 wolves in the area. If the rate increases continually, how many wolves will there be in 5 years? And then we want to know, as a second part of the question, how many years will the population double? Alright, so what we know in the first place, again, we have y equals c times 1 plus or minus r to the t. So our model is going to be y equals our initial number of wolves is 42. We're increasing by 3.5% a year, so that's plus 0.035 to the t. Now they want to know how many we're going to have in 5 years. That's pretty easy. So y is equal to 42, 1.035 raised to the 5th power. That's just a calculator. The answer we get here is 49.88. Can't have a 0.88 of a wolf, so we just say we round to the nearest whole number, or not even round to the nearest whole number. We've got to truncate, so we have 49 wolves. Now, the second problem is more complex in that we want to know when the population doubles. So we want to know when we go from 42 to double that. So 84 is equal to 42 to the 1 plus 0.035 to the t power. We want to solve for an unknown variable, and at this point we really don't know how to do that. The only thing we could do is isolate this exponential. So we have 2, I divide by 42 to both sides, is equal to 1.035 to the t power. Now, in order to solve for this, we're going to have to do some calculator work. So let's get those out. So we can see here that this is just going to be an exponential equation. We're going to type into our calculator 1.035 raised to the t, or in this case raised to the x, is the same thing. And then I'm going to graph another equation of y equals 2. Now when we graph these, and we can just graph this, I guess, in the standard window, that'd be fine. So zoom 6. And you'll notice there's our exponential. It's starting to rise. And there's another line. We see this doesn't intersect, so it's going to take a while for this to double, since it took 5 years for the population to raise 7 wolves. We want to raise a total of 42 wolves. So what I'm going to do is I'm going to extend my window. And I'll go quite a bit. Extending my window means I've got to change my x value, and we'll go from -10 instead of to 10 to 100. See if this will happen in 100 years. Most likely it will, but we just want to look at it. So I graph this now, and there's my exponential, and you'll notice there's my number 2. So if I find this intersection, I can find out how long it took for those two equations to be equal. So I go second, calculate, intersect, and first curve, enter, second curve, enter, and third curve, find my intersection. And it's about 20.14 years or 20.15 years is my intersection. This is going to be my answer here. So x equals 20.15 years. Those are all our examples for today. Fill out your lesson summary and do your Connect Ed.